The history of Mercury, the smallest and most hidden planet. Mercury is the first of our series of documentaries dedicated to the planets of the solar system, comprehensively describing their history and characteristics. It's the innermost planet of our solar system, so close to the Sun that it's almost always hidden in its blinding glare. We won't limit ourselves to describing the most well-known characteristics of this small planet. We'll go beyond, exploring its peculiar orbit that confirmed Einstein's theory of relativity, its strange relationship between day and year, its crater-riddled surface, and the surprising discoveries that continue to amaze astronomers. Comprehensive means exactly this: a detailed account, rich with information and insights that will lead you to see Mercury with new eyes, appreciating its complexity and hidden charm. Mercury is a planet of contrasts and mysteries. The first world of our solar system, so close to the Sun yet capable of hosting ice in its polar craters. So small it almost seems like a moon, yet so dense it harbors a disproportionately large metallic core. So slow in its rotation that a Mercurian day lasts 2 of its years, yet so quick in its orbit that it completes a full circuit around the Sun in just 88 Earth days. Its surface, marked by countless craters, is an open book on the evolution of the solar system, a cosmic archive etched in rock just waiting to be deciphered. But let's proceed in order and get to know this planet better through its numbers. With a diameter of just 4,879 kilometers or 3,032 miles, about 38.3% of Earth's, Mercury is the smallest planet in the solar system since Pluto was reclassified as a dwarf planet. Its mass is approximately 5.5% of Earth's, but despite its small size, its density is surprisingly high, 5.43 grams per cubic centimeter, or 338.4 pounds per cubic foot. Second only to our planet, suggesting a metallic core that occupies a full 60% of its total volume. Mercury orbits the Sun at an average distance of 57.9 million kilometers, or 36 million miles, 0.39 astronomical units, completing a revolution in 88 Earth days. Its orbit is the most eccentric of all planets, with a value of 0.21 that varies its distance from the Sun from a minimum of 46 million kilometers, or 28.6 million miles, to a maximum of 70 million kilometers, or 43.5 million miles. The planet rotates on its axis in 58.6 Earth days, with an axial tilt of just 0.03 degrees, practically perpendicular to the orbital plane. The temperature on the surface varies dramatically from a scorching 427 degrees Celsius or 800 degrees Fahrenheit at the equator during the day to a frigid minus 173 degrees Celsius or minus 280 degrees Fahrenheit during the polar night, the most extreme temperature range in the entire solar system. The surface gravity is 0.38 times that of Earth. If you weigh 154 pounds on Earth, you would weigh just 58.5 pounds on Mercury. This cold, objective data doesn't tell the true story of this small, rocky world. However, its biography is literally written on its skin. Lacking a significant protective atmosphere and geological processes that continuously renew its surface, Mercury preserves, like scars, the traces of every cosmic encounter in its long existence. And the craters that dot its surface are testimony to a series of violent impacts that occurred about 3.9 billion years ago in a period known as the Late Heavy Bombardment. It's not easy to investigate the early phases of Mercury's life because it's the most hidden planet in the solar system. Studying it thoroughly, as we'll discuss later, is a challenge even with space-age technology. In the era when astronomers can only observe it with Earth-based telescopes, getting information about Mercury was almost impossible due to its position, being the innermost planet of the solar system. To see it from Earth, we're forced to look towards the Sun. Hidden in the Sun's glare like a frightened child, Mercury is difficult to see in the blinding light of our star and peeks out only occasionally for short periods. From our position, we see Mercury moving from one side of the Sun to the other as it orbits. For about a month, the planet is visible as an evening star at twilight, low on the horizon after sunset. For another month, it disappears in the Sun's glare. Then it becomes a morning star, visible before dawn for the next month. After that, it disappears for another month behind the Sun and finally returns to its initial position. It takes 116 days to complete this cycle. Initially, ancient Greek astronomers believed that Mercury's evening and morning appearances belonged to two different planets, which they called Apollo and Hermes. It seems the mathematician Pythagoras, around 500 BCE, realized that the two planets were actually one. He probably noticed they had a similar appearance, moved at the same speed, and crucially, whenever Apollo became visible, Hermes disappeared and vice versa. The name Hermes was the one that prevailed, so much so that even today in Greece the planet is called that. Elsewhere, the name Mercury spread, which was the Roman equivalent of the Greek god Hermes. Like all planets, Mercury follows an elliptical orbit around the Sun, which occupies one of the two foci of the ellipse. This geometry, so different from the perfect circle imagined by astronomers before Johannes Kepler, implies that the distance between the planet and our star varies continuously during its revolution. Like a pendulum that accelerates at the lowest point of its oscillation, Mercury also modifies its speed, faster when close to the Sun, slower when farther away. The parameter that measures this variation is called the eccentricity of the ellipse, and it's a number that ranges from 0 in the case of no variation, that is, if the orbit is in fact a perfect circle, to almost 1 if the ellipse has a long, narrow shape. The eccentricity of Earth's orbit, for example, is 0.017, almost circular. Mercury's eccentricity, however, is 0.2056, making it the planet with the most eccentric orbit of all. This means that its distance from the Sun is extremely variable, ranging from 46 to 70 million kilometers, or from about 1/3 to almost half the distance between Earth and the Sun. Early studies. First hypotheses. Due to the difficulties of observation, even in the telescopic era, Mercury remained for a long time a little-studied planet. The first attempt to map its surface was toward the end of the 19th century. The Italian astronomer Giovanni Virginio Schiaparelli, the same one who observed the canals on Mars, who was also the first to hypothesize that Mercury's rotation period was equal to its revolution period, just under 88 Earth days. The work of mapping the planet was then continued and expanded by the Greek astronomer Eugene Michel Antonati, who in 1934 published the first detailed maps of its surface features. But to begin an in-depth understanding of the planet's morphology and internal structure, we had to wait until the second half of the last century, first with Earth-based radio and optical observations, then with space missions. The first important discovery was that, contrary to what Schiaparelli had initially proposed, the rotation period is not synchronous with the revolution period, but that the two are in 3:2 ratio. In other words, this means that the planet rotates on its axis 3 times for every 2 orbits around the Sun. The experimental data from the early 1960s provided by both Soviet and American radio observations was indeed about 59 days for the rotation period, compared to almost 88 for the revolution period. It was the Italian astronomer Giuseppe Bepi Colombo who suggested that a 3:2 resonance between the two periods relative to the Sun was a stable solution, despite the astonishment of much of the astronomical community, convinced that the 1-to-1 resonance, synchrony between the two motions as observed for our Moon, was the more likely scenario. At the origin of this phenomena is the force of gravity that is exerted reciprocally between the celestial bodies involved, and in particular the tidal forces, which act differently between the different parts of the same body. For example, for Mercury, the greater attraction by the Sun of the hemisphere facing the star versus the lesser attraction felt by the opposite hemisphere. This action is always dissipative and slows down the rotation motion until it reaches an equilibrium solution, such as the 1-to-1 resonance for the Moon relative to Earth, or the 3-to-2 resonance of Mercury relative to the Sun. But be careful, all of this is not without consequences for the day-night cycle of the small planet. In practice, because of this very particular relationship between the rotation period and the revolution period, combined with the high eccentricity of the orbit, a potential Mercurian inhabitant would have to wait 176 days before seeing the Sun return to the same position in the sky. During the course of a Mercurian day, they would see the Sun rise in the east and advance very slowly across the sky, about 3 times slower than the sidereal motion of stars, increasingly growing in apparent diameter. Near the meridian, the Sun would slow down even more until it stopped completely. Then the Sun would perform a double reversal of motion before resuming its journey toward the western horizon, which it would reach 88 days later, returning to its original dimensions. Other observers, located at points with a different longitude, would see different but equally bizarre movements. At midday from certain longitudes, the Sun may appear 3 times as large as it does from Earth, and it is 7 times brighter. Nevertheless, the surrounding sky is black and star-speckled inasmuch as Mercury does not have an atmosphere in the traditional sense. It is a lonely sky without a satellite, nor even rings orbiting the planet. The surface. Are we on the moon? Mercury's surface appearance, well studied only following dedicated space explorations, is not very dissimilar from that of the moon, alternating between regions rich in craters and smoother, flatter areas that suggest past volcanic activity, like the one that gave rise to the lunar seas. On the other hand, the lack of an atmosphere causes the absence of erosive processes and surface features that can be preserved for billions of years. The structures that dominate Mercury's surface are impact craters. As on all other celestial bodies in the solar system with a solid crust, craters are of all sizes, and their topography depends on their diameter. Below 10 kilometers or 6.2 miles, there are only simple bowl-shaped craters. Between 10 and 130 kilometers or 6.2 and 80.8 miles, craters have a central peak. Between 130 and 310 kilometers or 80.8 and 192.6 miles, in addition to the peak, a central ring also appears. While beyond 310 kilometers in diameter, multiple rings appear. At equal diameter, Mercury's craters have an ejecta blanket that is 0.65 times smaller than that of lunar craters, probably an effect of the greater acceleration of gravity compared to the Moon. And then there are the smooth plains, which are the equivalent of the lunar Maria. About 40% of the hemisphere photographed by Mariner 10 is occupied by these plains, in 90% of cases associated with impact basins. From the analysis of the number of craters superimposed on the smooth plains, it can be deduced that these must have formed at the end of the primordial bombardment period, and their origin is probably volcanic. The intercrater plains, that is, those included between the craters, are more difficult to interpret than the smooth ones. On the lunar highlands, craters are so densely packed that they overlap each other. This is the phenomena of crater saturation. On Mercury, large portions of cratered surface are not saturated, and between one crater and another there is relatively flat terrain. Compared to the lunar highlands, craters with a diameter below 40 kilometers are scarcer in Mercury's plains. The distribution of intercrater plains and the lack of impact basins of which they could constitute the ejecta argue in favor of their volcanic origin. Another peculiar feature of Mercury's surface are the lobate scarps. These are abrupt crustal fractures ranging from 20 to 500 kilometers, or 12.4 to 310.7 miles in length, with heights between 100 and 3,000 meters, or 328 to 9,843 feet. The most notable of these structures is Discovery Rupes. In Latin, scarp is called rupes. There are few craters superimposed on the scarps, which therefore must have formed relatively late in the planet's history. In any case, only after the formation of the intercrater plains and the larger basins. The most plausible explanation for the formation of this system of fractures is that it is the result of the contraction of the planet's crust due to cooling. They would therefore be compression faults. A decrease in the planet's radius of just 2 kilometers or 1.2 miles is sufficient to account for the system of fractures that is observed. Nothing similar exists on the other terrestrial planets. In addition to the scarps, other elongated structures, the troughs, are also present on Mercury's surface. Troughs are structures a few hundred meters or several hundred feet deep, about 10 kilometers or 6.2 miles wide, and more than 100 kilometers or 62 miles long. Unlike scarps, troughs are aligned in 3 preferential directions: northeast, northwest, and north-south. The troughs form what is called Mercury's grid. Similar structures are also observed on the Moon and are attributed to the slowing of the planet's rotation period due to solar tides. Among the records cited earlier, Mercury also holds that of having one of the largest craters in the solar system in relation to the size of the planet that hosts it. The Caloris Basin, or Caloris Planitia, an impact crater almost 1,600 kilometers or 995 miles in diameter. Like the large lunar craters, Caloris Planitia is a lava plain and is surrounded by a ring of mountains up to 2,000 meters or 6,562 feet high. It is located at Mercury's equator, the hottest area of the planet, where the sun's rays are strongest. Not coincidentally, its name means plane of heat. Caloris Planitia was created by the impact of an asteroid about 100 kilometers or 62 miles in diameter, probably 10 times larger than the asteroid that caused the extinction of the dinosaurs on Earth. The impact was so violent, as evidenced by the crater walls, raised almost 2 kilometers or 1.2 miles above the surrounding terrain, that the effects propagated throughout the planet, generating seismic waves that traversed the entire planet, causing earthquakes at the diametrically opposite point, where a vast area called weird terrain formed. This region, characterized by a series of irregular hills and small craters with a conformation different from any other observed on the planet, was probably generated by the meeting of seismic waves that propagated on the planet following the impact, eventually breaking up and raising the previous terrain, although some hypothesize that it is made up of materials that fell back onto the planet's surface once they were lifted by the collision. Then the seismic waves returned, and the roar of the earthquake filled the planet, making it vibrate like a tuning fork for hours or perhaps days. The vibrations cracked Mercury's surface, from which incandescent lava began to emerge. Volcanic activity affected large areas, which were invaded by lava flows and transformed into smooth plains, the exact opposite of the chaotic terrain. The mountains trembled, landslides fell from their sides. The consequences of the impact extended to the entire planet. The formation of Caloris Planitia was a terrible event with global effects. The impact of the asteroid profoundly disrupted Mercury. If it had been larger, it would have literally torn the planet to pieces. The internal structure, the core, the magnetosphere, truly torn to pieces? Well, perhaps not. Mercury is in fact the planet with the highest density of iron, and it would therefore not be easy to reduce it to shreds. Nearly 3/4 of its diameter is occupied by a large ferrous core, 3,600 kilometers or 2,237 miles, compared to a total diameter of almost 4,900 kilometers or 3,032 miles. This core would occupy 40% of the planet's volume and would constitute a full 70% of its mass. In comparison, Earth's core is only 17% of our planet's volume. Proportionally, Mercury has the largest iron core of all the terrestrial planets. It's not easy to understand why, especially since theoretical models on the birth of the solar system predict lower densities. It's possible that the Sun, at the beginning of its existence, swept the innermost part of the solar nebula more energetically than predicted, allowing only heavy metals to aggregate. An alternative is the impact of Mercury with a large asteroid capable of removing the outer mantle while leaving the iron core intact. In this scenario, the impact would have occurred after the planet's differentiation. The rest of the planet is composed of a mantle and a crust made of materials similar to those of Earth's crust, especially silicon-based. Despite many thinking that Mercury's rotation was too slow for it to develop a magnetic field, the planet actually has one, dipolar and global, generated by a dynamo effect similar to that of Earth, due to the rotation of the planet's large liquid core. Although faint, its intensity is about 1% of Earth's. It is still intense enough to produce a magnetosphere and thus deflect much of the incoming solar wind. And the atmosphere? The planet's atmosphere, composed of hydrogen, helium, sodium, potassium, and calcium, is extremely rarefied and therefore does not contain enough gas to reduce the heat and light it receives from the sun. Moreover, the slow rotation of the planet exposes different areas of the surface to direct sunlight for long periods. This leads to the highest temperature range among all the planets in the solar system. As we've already mentioned, Mercury's distance from the Sun is highly variable, so the amount of light and heat reaching the planet can become at times more than double or less than half. Thus, the temperature also changes enormously depending on the time of day and the latitude considered. During the day, the surface temperature ranges from -183 degrees Celsius at the poles to 427 degrees Celsius at the equator. At night, heat disperses quickly from the bare rocks, and the surface temperature can drop to -200 degrees Celsius. At Mercury's equator, common metals like lead and tin would melt, and the plastic of a potential lander would end up melting or decomposing. Obviously, all this would be fatal for electronic instrumentation, with plastic-coated components, metal cables, and solders, unless adequate measures were taken to address the problem. So far, however, no one has found a practical solution. Mercury confirms general relativity. It's impossible to talk about Mercury without mentioning the fundamental contribution of this planet to the confirmation of the theory of general relativity. Observations show that every time it completes a circuit around the Sun, its elliptical orbit rotates in space, advancing the perihelion, that is, the point of maximum approach to the Sun. As we well know, Newton's theory of gravitation is extraordinarily precise in describing planetary orbits and the position of planets along their path. In the case of Mercury, however, it was noticed in the 19th century that the measurement becomes mysteriously imprecise. At the end of each circuit around the Sun, the planet was found to be in a position slightly different from that predicted by Newtonian calculations, and after a few decades, the differences accumulated, resulting in a significant deviation. Normally, as happens for all other planets, albeit to a much lesser extent, the major axis of the ellipse slowly rotates around the Sun, which is at one of the foci. This rotation of the orbit is called precession, and it is predicted by Newtonian theory. All planets, in fact, are characterized by this phenomenon, caused mainly by the gravitational attraction of other planets and especially that of the Sun. The precession speed can be calculated with Newton's theory of gravitation, which provides an almost exact answer for all planets except Mercury and Venus. During the 19th century, a precession of 5,600 arc-seconds, approximately 1.6 degrees per century, was measured for Mercury's orbit. However, calculations based on Newton's theory explained only 5,557 arc-seconds per century. What else was missing from the theoretical model to justify those missing 43 seconds? An arc-second is 1/3600th of a degree, so it's a minimal difference. But it couldn't be ignored, and it had become quite a headache for scientists of the time. Before having a satisfactory explanation, the French astronomer Urbain Le Verrier, the same one who had predicted the existence of Neptune, hypothesized that the anomaly was due to an as-yet unknown planet closer to the Sun than Mercury. This hypothetical planet, named Vulcan, was the object of an astronomical hunt that lasted decades, with alleged observations and denials, until in 1919, Albert Einstein offered an explanation. In his general relativity, gravity is an effect of the curvature of space-time, and a planet's orbit is not a static ellipse but would rotate anyway, even in the absence of the gravitational attraction of other planets. The closer to the Sun, the faster. And when he calculated Mercury's precession using his relativistic model, the German scientist astonished the scientific world by accounting for all 5,600 arc-seconds per century. The first space missions, Mariner 10 and Messenger. The proximity to the Sun, even in perspective, has always made the observation and study of this small planet very difficult, which has thus always remained on the margins of general attention, and partly also of scientific attention. For example, there are no photos of Mercury taken by the Hubble Space Telescope, which, to safeguard its sensors, has never pointed its photographic instrumentation in its direction, nor in that of Venus. And only 2 probes have visited Mercury, 3 with the recent Bepi Colombo still operational. It may be the closest of the planets, but it's also terribly difficult to reach. How come? Well, the problem is that heading towards Mercury also means plunging headlong into the sun's gravitational well, which would attract the spacecraft to itself until it reached such a high speed as to prevent insertion into Mercury's orbit. The spacecraft would need to find a way to slow down, but this would mean carrying enormous amounts of fuel. The only other way is to slow down by relying on numerous gravitational assists with Venus and with Earth itself, with changes of course that, however, inevitably lead to greatly extending the duration of the journey. This explains the scant attention shown to the planet by the various space agencies. The first probe to visit Mercury was NASA's Mariner 10 in the first half of the 1970s, which took only 134 days to reach Mercury. The second was Messenger, with orbital insertion occurring in 2011 after a full 7 years of travel. The enormous disparity in flight times between the two missions depends on the fact that Mariner 10 limited itself to flying over the planet, without trying to orbit around it. It was attracted by the sun's gravitational field and slowed down only by a flyby with Venus. It had a very rapid encounter with Mercury. Messenger's objective, on the other hand, was to orbit the planet, which it managed to do only after an infinite wandering between Venus and Earth in an attempt to dissipate energy and speed. Mariner 10, launched by NASA on November 3, 1973, to explore Venus and Mercury, was able, thanks to 3 close passes with the planet made between 1974 and 1975, to provide us for the first time with detailed images of its surface, as well as to discover the existence of the planetary magnetic field. Its most important record, however, is that of being the first probe to use the gravitational assist of a planet, Venus, to be directed towards another planet, Mercury. We recall that the slingshot effect consists of exploiting a planet's gravity during a close passage to accelerate or decelerate a probe, or even to modify its trajectory. Depending on the relative position of the orbits and the relative velocities, a probe can thus vary its orbital motion without using its engines, and therefore without consuming fuel, making possible trajectories and objectives otherwise impossible to reach for reasons of cost or time. And finally, 3 incredible facts. In 2008, the Messenger probe, launched in August of 2004, revealed that the planet possesses a long trail of sodium and calcium atoms extending over 2.5 million kilometers, or 1.55 million miles, into space. This phantasmagoric tail, invisible to the human eye but now detectable even with amateur instruments, is generated by the interaction between the solar wind and Mercury's tenuous exosphere. The charged particles of the sun strike the planet's surface, causing atoms to jump, which are then pushed by the pressure of solar radiation, creating this extraordinary cosmic appendage. Like a planet playing at being a comet, Mercury reminds us that even the seemingly simplest celestial body can hold unexpected wonders. Like this other one we're about to tell you about. Well, believe it or not, despite what common sense tells us, it would be Mercury, not Venus, that is the closest planet to Earth. The relative position of the orbits is always as described in school books, but the distance separating the planets changes if calculated in relation to time. In practice, the orbits of Venus and Earth are separated by a distance of 0.28 astronomical units, while Mercury's orbit is 0.61 AU from Earth's orbit. Put this way, there would seem to be no doubt from a geometric and absolute point of view, Venus is indeed the planet that comes closest to Earth. But if the calculation is made with respect to time, that is, if one counts over a long enough period of time what the average distance of the two planets is, then it is discovered that Mercury spends a longer time in the vicinity of Earth than Venus does, so much so that the average Mercury-Earth distance in the long term is 1.04 AU, while that of Venus is 1.14 AU. It's a bit like what happens to us in everyday life. Between an uncle who comes to visit us once a year and then returns to his home 100 kilometers away, and the neighbor who lives all year round 100 meters from our house, who do you think is, on average, closer to us? Finally, one of the most poetic aspects of Mercury is related to the slowness with which the terminator, the line separating day from night, moves across its surface. Due to Mercury's peculiar rotation, So slow compared to its year, the Terminator advances at a speed of just 3.6 kilometers per hour or 2.2 miles per hour, comparable to that of a person walking at a brisk pace. This means that a hypothetical Mercurian explorer could, in theory, walk along the Terminator, remaining perpetually suspended between the scorching day and the freezing night, in an eternal twilight. Imagine being able to walk along the border between light and darkness, chasing a sunset that lasts for Earth decades, while behind you a dawn drags itself with the same indolence. On Mercury, this is not just a romantic dream, but a direct consequence of its orbital laws, a mathematical poetry written in the language of celestial physics. The story of Venus, a knife hidden among feathers. It's time to turn our gaze towards another fascinating neighbor of Earth, Venus, the planet that has ignited human imagination for millennia. Known as the morning star or the evening star, Venus is a world of contradictions, a place that almost seems like Earth's twin, but hides a hellish face beneath its brilliant surface. In this new chapter of our series, we won't just describe its well-known features, we'll go beyond, exploring its geological history, toxic atmosphere, extreme conditions, and the latest scientific discoveries that continue to astonish astronomers worldwide. Exhaustive truly means that a detailed narrative, rich with information and insights, that will make you see Venus with new eyes, appreciating its complexity and allure. Despite often being overshadowed by the popularity of Mars or the gas giants like Jupiter and Saturn, Venus is a planet that, especially in this historical phase, deserves our full attention. It's a natural laboratory for studying runaway greenhouse effects, a warning to understand the delicate balances that govern planets, and perhaps one day it might even reveal clues about the possibility of life in extreme conditions. Alright folks, you decide whether Venus deserves to be called Earth's twin sister or not. I don't hear any dissenting voices, and indeed with an average diameter of 12,103 kilometers, about 7,520 miles, roughly 95% that of Earth, and a mass that's 81.5% of Earth's, who could deny that in terms of size and physical characteristics, Venus and Earth look like two planets separated at birth? These similarities also extend to their density, 5.2 grams per cubic centimeter for Venus, compared to Earth's 5.5 grams per cubic centimeter, and surface gravity. On Venus, you'd weigh about 90% of what you do on Earth. You'd feel just a bit lighter. But it's not just about size. The two planets also formed in the same region of the solar system, which means they have very similar chemical compositions, with one little difference. While Earth turned into a green and blue paradise, Venus turned into a toxic inferno, an incredibly hot, dry world that's absolutely hostile to any form of life, to the point where one of the current goals of planetary scientists is to understand how our twin transformed this way. It's not just scientific curiosity. Understanding this could teach us something about the climate changes happening here on Earth too. But let's take it step by step. Venus is, after the Moon and the Sun, the brightest object in the sky, and its brilliant presence in the warm hues of twilight has always sparked curiosity and admiration. The planet is called Hesperus when it's the evening star and appears after sunset, and Lucifer when it's the morning star and precedes the sun at dawn. This happens because, like Mercury, Venus is one of the inner planets of the solar system, meaning its orbit around the sun is closer than Earth's. And due to orbital geometry, this means we'll never see Venus more than 47 degrees away from the sun, maximum elongation. For Mercury, the same thing happens. Its maximum elongation doesn't exceed 28 degrees. Its brightness surpasses Sirius by 20 times and Jupiter by 6 times. And at its brightest, it can't even cast a noticeable shadow on Earth. Even in broad daylight with a clear sky, it's possible to spot it with the naked eye. Its particular brightness is due not so much to its size, similar to Earth's, but rather its frequent proximity to our planet and the reflective nature of its cloud cover. And because of those impenetrable clouds, until half a century ago, Astronomers had to make do with calculating that Venus orbits the Sun in 224.7 days, at an average distance of 108 million kilometers or 67 million miles, about 0.72 times the Earth-Sun distance. And that its orbit is the least eccentric of any planet, deviating from a perfect circle by only about 1 part in 150. For Earth, just to understand, this value is 1 to 60, while for the most eccentric orbit, Mercury's, the value is 1 to 5. And while Venus and Earth dance around the Sun, the distance between them varies from a minimum of 42 million kilometers or 26 million miles to a maximum of 257 million kilometers or 160 million miles. Similar to the Moon, the portion of Venus's surface visible from Earth is not always fully illuminated, and the variation in illumination during its orbit creates phases. As these phases change, so do the apparent diameter and brightness perceived by an observer on Earth. The full phase, during which the side of the planet facing Earth is fully illuminated, occurs when Venus is in superior conjunction with the Sun and is not visible from our planet. At inferior conjunction, Venus's apparent diameter reaches its maximum value of 66 arcseconds, and it's in its new phase, with the side facing Earth almost completely in shadow. But of course, Venus's phases aren't an intrinsic aspect of the planet, but a consequence of its orbit and its position relative to us and the Sun. So what's its real nature? Because of the thick, continuous clouds, nothing was known about it before the 20th century. For example, did the planet rotate, and at what speed? Well, it's hard to believe now, but Venus's rotation period was measured using the Goldstone radio telescope in California only in 1961, and its retrograde motion was definitively confirmed only in 1964. Yes, you heard that right. Until the 1960s, when the era of radar measurements began, we didn't even know the rotation period of our closest planet, nor the tilt of its axis. And the radar measurements delivered astonishing data, revealing that Venus's rotation is truly unusual. The planet rotates around its axis very slowly, completing one rotation approximately every 243 Earth days. It's the only planet in the solar system that takes longer to rotate around its axis than to orbit the Sun. These two motions combine in such a way that one day on Venus, the time it takes for the Sun to appear directly overhead, set, and then rise again directly overhead lasts about 117 Earth days. Because of its slow rotation, Venus has retained an almost spherical shape compared to Earth and most other planets. The rotational force of a planet generally causes a bulge at the equator and flattening at the poles. These distortions are minimized on Venus. Then there's the fact that Venus rotates in a retrograde motion, meaning in the opposite direction to most other planets in the solar system. 6 of the 8 planets rotate counterclockwise as viewed from above the North Pole, while only Venus and Uranus rotate clockwise. For an observer on Venus, the Sun would appear to rise in the west and set in the east, if you could see through the thick clouds. Venus's axis of rotation is tilted by only about 3 degrees relative to its orbital plane. This means the seasonal variations on the planet are likely very mild. Unlike Earth and most other planets, Venus does not have a global magnetic field, and this might also stem from its extremely slow rotation. Scientists think that a planet's rotation helps drive fluid movements in its core that generate a magnetic field. And there's more. Although there's no unanimous agreement on this, Venus's rotation seems to be somehow synchronized with Earth's position along its orbit. So much so that when the two planets get close, Venus always shows us the same face. A phenomenon surely due to a still unresolved combination of gravitational interactions. But let's move on, or rather, let's stay a bit longer in the 1950s, when astronomers could only speculate about what Venus might be hiding under its blanket of clouds, and dream of a warm, humid world like our rainforests, the only planet besides Earth likely capable of hosting even evolved forms of life. A romantic dream destined to clash very soon with a harsh reality. Under the absolute white of its clouds, Venus hid a dark secret, a horrendous face, and an infernal environment where it's difficult, if not impossible, to imagine any form of life. As it would soon become known, Venus's surface is covered with black, scaly, sterile volcanic rocks, crisscrossed by solidified lava rivers expelled from hundreds of volcanoes. The atmosphere is very dense. The surface atmospheric pressure is 90 times that of Earth, similar to being 1,000 meters or about 3,280 feet underwater. That's roughly the maximum depth at which our submarines operate, though research bathyscapes and rescue vehicles can go much deeper. The atmosphere is mostly composed of carbon dioxide with nitrogen and traces of sulfuric acid, hydrogen chloride, and hydrogen fluoride. These substances precipitate on the surface as acid rain, quickly destroying machinery like spacecraft landing on the surface. The clouds aren't made of water droplets like on Earth, but sulfuric acid droplets. The sun's rays weakly filter through the dense, sulfurous atmosphere, casting an ugly, yellowish tint on the surface. Before the space age, few of these details were known. Only the general composition of the atmosphere, its high density, and its temperature, which is undoubtedly the least favorable aspect for life on the planet. In 1956, Cornell H. Mayer, a pioneer in radio astronomy, and his colleagues at the United States Naval Research Laboratory observed Venus in the microwave frequency. They discovered that its surface had a much higher temperature than Earth's, so hot it could melt lead. The first spacecraft to visit Venus was Mariner 2, an American probe that performed a flyby in 1962. The initial plan was to launch the probe with a new rocket, which had some development issues. So they had to settle for an earlier, smaller rocket with a lower payload capacity. Consequently, the instrumentation on Mariner 2 was significantly reduced from the original plan. Nevertheless, the mission was successful. The radio astronomical studies from 6 years earlier had probed Venus's atmosphere from afar, but couldn't provide a definitive answer. The most important scientific result of Mariner 2 was confirming up close that Venus's surface temperature is very high, over 400 degrees Celsius or 752 degrees Fahrenheit. In the 1960s and 1970s, other Mariner probes were launched, but we owe our detailed knowledge of Venus's surface mainly to a series of Soviet landers that parachuted below the clouds. In the 1960s, NASA focused on the Apollo program, which would put the first man on the moon, in line with the challenge issued by President Kennedy in a famous 1962 speech. We chose to go to the moon. Meanwhile, the Soviet Union dedicated most of its space missions to the closest planets, Venus and Mars. The scientific exploration of Venus began in 1967 with the Venera spacecraft series, initially designed by aerospace engineering pioneer Sergei Korolev. Like Mariner 2, the first Venera probes limited themselves to flybys of the planet to gather data using remote sensing techniques. Later, other vehicles were parachuted into Venus's atmosphere to directly measure its properties during descent, which lasted about an hour. The probes were battered by strong winds, reaching up to 320 kilometers per hour, or about 200 miles per hour. This is because compared to the solid planet, Venus's atmosphere rotates very quickly. As we mentioned before, the planet completes a full rotation on its axis in 243 days. But the higher regions of the atmosphere at the equator take only 4 days to circumnavigate the planet, with wind speeds varying from around 360 kilometers per hour or about 220 miles per hour in the upper atmosphere, to just a light breeze at the surface. To withstand the intense heat and corrosive acids in the atmosphere, the Venera landers had to be heavily armored. They looked more like sturdy steam locomotives than spacecraft. The engineers who built them knew they would be parachuted into an environment with prohibitive conditions, including nightmarish atmospheric pressure. The first to successfully land on Venus was Venera 7 in 1970. Something went wrong during the descent, which was much faster than expected. The spacecraft hit the ground at the speed of a car in a severe accident, damaging the instruments. Fortunately, the lander was robust and didn't get destroyed. It only toppled over, but the side with the radio antennas ended up pointing away from Earth. Despite this, for 20 minutes, a faint radio signal managed to send information about the planet's surface. Venera 8, however, was the first probe in the entire series, 1972 to 1984, to land successfully. Typically, after landing, each vehicle would last at most an hour before the heat and atmospheric conditions caused the instruments to stop functioning. The missions showed that Venus's thick clouds didn't reach the planet's surface, but visibility of the landscape was still limited. The landers spotted hills no more than 3 to 5 kilometers or about 2 to 3 miles away, while at their feet they saw black slabs of magmatic rock, scattered and cracked. The nature of the farther landscape remained mysterious. Studying Venus in the classic way by trying to light the environment with spotlights had strong limitations. Radars, however, could penetrate the clouds, forming the basis of subsequent exploration. After some experimental investigations, significant progress was made with 2 Venera missions, Venera 15 and Venera 16, both launched in 1983. These probes were equipped with wide coverage radar systems, with a spatial resolution of about 1 kilometer or 0.6 miles, and a height resolution of about 50 meters or 165 feet. The missions identified recognizable volcanic features and other decidedly unusual. Venus had shield volcanoes and numerous volcanic cones, structures we know well because they are also present on Earth. But there are others that don't exist on our planet, such as coronae, large circular structures that had previously been mistaken for meteorite craters filled with lava. Not exactly volcanoes as we understand them on Earth, but rather typical annular structures created by liquid lava escaping from an underlying caldera and forcing its way through cracks in the lithosphere. A similar process on Earth formed the volcanic islands of Hawaii. In areas where these coronae form, the crust undergoes concentric collapses that produce rings with diameters ranging from 100 to 1,000 kilometers, or about 62 to 621 miles. Over 500 coronae have been identified on Venus, many of them located on the highest plains, the regions most affected by crustal compression. The authors of the study propose examining the morphology of these coronae using ultra-high-resolution simulations and using them as indicators of recent outbursts of magmatic material from the mantle. Then there are the arachnoids, collapsed domes with radial cracks that resemble spider legs. Both these structures signal the underground presence of stationary hotspots, which generate bubbles of magma within the planet's crust. Venus doesn't have moving tectonic plates colliding with one another, so its volcanoes aren't aligned like those on Earth along the Pacific Ring of Fire. They're scattered pretty much everywhere. The breakthrough in studying Venus's surface came with an important mission, the first interplanetary mission by NASA after an 11-year hiatus. Launched from the Space Shuttle in 1989, the Magellan probe reached Venus in 1990 and orbited the planet for 4 years. Its name was a clear homage to Ferdinand Magellan, the explorer who first circumnavigated Earth. The probe's central body, the module, was ingeniously assembled in a low-cost operation using spare parts from previous missions, and it was equipped with radar to map Venus. To outdo the Venera missions, NASA boosted the radar resolution from 600 to 100 meters, about 200 to 328 feet, allowing Magellan to see geographical details roughly the size of a soccer field. The probe didn't orbit along Venus's equator. It traveled from north to south and then back up, flying over the poles and completing an orbit every 3 hours, while its orbital plane remained fixed in space as the planet rotated beneath. In doing so, the probe observed almost the entire planet, mapping one slice after another and creating a radar image that revealed the ups and downs of the terrain, that is, its geomorphology. Venus's glory was unveiled, and its secrets were finally in plain sight. Magellan revealed that almost 3/4 of Venus's surface is a volcanic landscape. There are almost 100 shield volcanoes similar to Hawaii's Mauna Loa, and hundreds of thousands of smaller, isolated volcanic cones like Mount Etna. In general, Venus's volcanoes cover larger areas, although they aren't taller than those on Earth. The tallest volcano, the Maxwell Montes Massive, reaches 11,000 meters, or 36,089 feet, comparable to the height of Mauna Loa measured from the ocean floor. The channels of solidified lava which flow down the slopes of these volcanoes appear as sinuous lines of irregular, distorted rocks, similar to lava flows on Earth but much longer and broader. These differences are probably due to variations in the composition of the surface rocks. Those on Venus must be more ductile. About 10% of Venus's surface is covered in dust that has accumulated on the plains, blanketing everything. This dust comes from the erosion of the highlands, which in turn is driven by chemical reactions between the rocks and the atmosphere. Since there isn't much water on Venus, only a little in the atmosphere, the erosion isn't caused by water as it is on Earth. Instead, it's partly due to wind, which lifts the dust and wears away the remaining rocks, and partly due to meteorite impacts that shatter the surface rocks and spread fragments everywhere. Venus is as rich in volcanic craters as it is poor in meteorite craters. Only about 1,000 meteorite craters have been identified, many fewer than those on Mercury and the Moon, both of which lack an atmosphere, yet many more than those known on Earth. Terrestrial craters have largely vanished because they are eroded by atmospheric phenomena and because the movement of tectonic plates continually renews the surface. On Venus, there are atmospheric processes, but no tectonic recycling. The reduced number of craters is partly due to the atmosphere protecting the surface from impacts, as meteors tend to disintegrate before reaching the ground. In fact, many craters appear in clusters, as if formed by fragments of a meteor that broke apart without being completely destroyed and fell together. However, the main reason for the scarcity of craters is that in terms of planetary age, the surface of Venus is as young as Earth's, despite lacking active tectonic plates. Perhaps in the past there were more craters, but they have since been covered by new volcanic material and now lie beneath the surface. By linking the number of craters to the frequency with which asteroids hit the planet today, astronomers have estimated that Venus's surface is about 500 million years old. This means 3 or 4 billion years or more of the planet's history remain hidden, a secret beneath its relatively fresh surface, a past wiped clean like a secret agent's changed identity. Has the renewal of the surface occurred gradually over the past 500 million years? Or did it happen all at once about 500 million years ago? It's likely that today there are some active volcanoes on Venus, and in a couple of cases, volcanic ash emissions have been observed. The recent European space mission, Venus Express, identified hotspots on the flanks of some volcanoes, suggesting that beneath their surfaces there are pools of glowing lava, even though no true eruption has ever been observed. Venus is geologically active, but not very much. This suggests that the period of intense volcanic activity dates back a long time. The volcanic activity that renewed Venus's surface was a catastrophic event. What was the cause? Was the entire planet consumed by the fire of volcanoes unleashing all the pent-up rage inside? Or was the lava flow triggered by an external factor? For now, this phase in Venus's history remains a mystery. The renewal spurred by volcanic activity wasn't the only global catastrophe to hit the planet. Today, no trace of water remains on its surface. But according to astronomers, when Venus formed 4.6 billion years ago, and for a period thereafter, it likely wasn't very different from Earth. In fact, it's reasonable to think that at birth, all the terrestrial planets, Mercury, Venus, Earth, Mars, shared similar conditions. Essentially, all newborns look alike. As they matured, however, these planets became distinct individuals, both because small natural differences grew over time and because they were educated in different environments. If it's plausible to support that liquid water once graced Venus's surface, delivered by asteroids and comets, then the planet likely also had an atmosphere made up of nitrogen, water vapor, carbon dioxide, and methane produced by volcanic eruptions. The carbon dioxide and methane would have created a powerful greenhouse effect, further amplified by water vapor as the oceans evaporated due to Venus's proximity to the Sun. The greenhouse effect is a property of certain gases in a planet's atmosphere. On Earth, it's crucial because it keeps the surface at a relatively constant temperature conducive to sustaining life. It was Joseph Fourier, the French mathematician and physicist, who discovered the greenhouse effect of Earth's atmosphere in 1827. Earth receives sunlight and absorbs about 70% of it. The absorbed energy warms the ground, the atmosphere, and the oceans. The warm masses then radiate heat back into space as infrared radiation, which is largely absorbed by greenhouse gases and clouds in the atmosphere. Rather than dispersing into space, the infrared radiation rises the temperature in both layers of the atmosphere. In this way, the heat from the ground and oceans can't escape, and the surface and lower atmosphere keep getting warmer, much like a greenhouse, and that's where the analogy comes from. From the very beginning, the greenhouse effect on Venus was much more intense than on Earth. The planet heated up to the point where its oceans completely evaporated. This happened long before the volcanic resurfacing wiped out any traces of those oceans, rivers, or water-formed minerals. All the water vapor that ended up in the atmosphere only worsened the original greenhouse effect, pushing the temperatures even higher. The atmospheric composition changed, and other greenhouse gases formed, like clouds made of tiny sulfuric acid droplets. As a result, the temperature kept climbing and so on. This explanation was proposed in 1961 by Carl Sagan, an astronomer at Cornell University, to account for Venus's extremely high temperatures. Its runaway greenhouse effect had spiraled completely out of control. Today, the greenhouse effect completely dominates Venus's climate, driving its temperatures up to 500 degrees Celsius or 932 degrees Fahrenheit. On Earth, by comparison, it only brings the temperature up to about 33 degrees Celsius or 91 degrees Fahrenheit, which, while considerable for our climate, is beneficial and not catastrophic. However, the human-produced or anthropogenic greenhouse gases generated by industrial activities in livestock farming, carbon dioxide from burning fossil fuels, and methane from cattle are causing Earth's temperature to rise, threatening to disrupt this delicate balance. The Paris Agreement of 2015 outlined the necessary steps to keep our planet's overall temperature from increasing more than 1.5 to 2 degrees Celsius, or 2.7 to 3 degrees Fahrenheit, above pre-industrial levels by limiting these emissions. Of course, no such controls have ever been applied on Venus, and its natural greenhouse gas emissions have increased far more dramatically than what we're experiencing here. Today, the planet is a hellish landscape of extreme temperatures and bare, arid, and sterile rocks. A horror movie scenario that vividly demonstrates the catastrophic effects of climate change. For Earth, a 2-degree increase in global temperatures might seem like a minor issue, especially compared to the 500-degree surge that Venus once experienced. But even such a small increase could prove disastrous, not necessarily for the survival of our planet, but at the very least for the future of our species. In the end, Venus stands as both a fascinating enigma and a dire warning. As we peel back its thick, acidic clouds and uncover the secrets of its runaway greenhouse effect, we're reminded of just how delicate the balance is between a habitable world and a hostile inferno. Venus may have lost its oceans long ago, and with them any chance for life as we know it. Yet its story is crucial for us here on Earth. It shows us that even small changes in our own atmosphere, whether from nature or human activity, can have catastrophic long-term consequences. Whether it's 15, 20, or 30 years from now, there's no doubt that our destiny will eventually lead us to Mars. We'll get familiar with the moon first, and then we'll take the big leap. In this exploration, the most challenging one humanity will face, there will be no room for even the slightest mistake. There will be no one to help our astronauts. They'll have to do everything on their own, relying solely on their skills and the resources on board to handle the inevitable emergencies. The members of the first crew to attempt this feat are probably already among us, perhaps very young and still unaware. Mars is the red planet, red like blood, a fitting color for the god of war it's named after. In the sky, the planet is easily recognizable. Nothing shines with that color and brightness except for the star Antares, whose name fittingly means rival of Mars. Of all the planets in the solar system, Mars is the most similar to Earth. It's significantly smaller with a diameter half that of Earth. It's also much colder and drier, but 4.6 billion years ago, it was like Earth, warm and wet, with a thick atmosphere and abundant water. If humans had been around on Earth back then, they would have looked up and seen a blue planet, not a red one. Everything changed around 4 billion years ago when things took a turn for the worse. Like Venus, Mars experienced a global climate catastrophe. The reason, unknown until recently, lies in its core. It's hard to determine this just by observing the planet through a telescope, although today even telescopes used by amateur astronomers can easily show the features of the disk of Mars. Galileo was the first to observe the planet with a telescope in 1610, but the instrument was too small and the view too blurry to distinguish surface features. The first surface feature of Mars was discovered in 1659 by Dutch astronomer Christian Huygens. He saw a dark triangular mark, drew it, and described it as a large pond. At the time, it was thought that the gray spots on the moon were oceans, seas, and Huygens followed that line of thinking. In reality, both topographical features are caused by the different coloration of certain minerals and rocks compared to the rest of the surface. By tracking the repeated appearances of this triangular mark, Huygens was able to determine the rotation period of Mars, its day. A Martian day is called a sol and lasts just 37 minutes longer than Earth's 24-hour day. Mars is twice as far from the Sun as Earth, and its year is much longer, 687 Earth days compared to our 365. The tilt of its axis is similar to Earth's, 25.2 degrees, compared to our 23.5. Consequently, day and night alternate just like on Earth, and so do the seasons, but winters are much colder and last longer. The orbit of Mars changes over time, and with it, the cycle of seasons and climate. Currently, surface temperatures range from 20 degrees Celsius during the day to minus 140 degrees Celsius at night. On Earth, the coldest place is Dome Fuji, a research station on the Antarctic Plateau where temperatures drop to minus 80 or minus 90 degrees Celsius at most. In 1666, Italian-French astronomer Gian Domenico Cassini discovered that Mars has polar ice caps. Through a telescope, these appear as white spots at the planet's poles. One grows while the other shrinks, and vice versa, depending on the changing seasons. The polar caps are deposits of ice and dry ice 2 to 3 kilometers thick, with steep cliffs at the edges. The surrounding plains are also covered with dry ice, solid carbon dioxide, which sublimates with the changing seasons. Sublimation is the process where a substance transitions from a solid to a gas without passing through the liquid state. As for water ice, it usually melts and turns into liquid before becoming gas, vapor, but it sublimates if the atmospheric pressure is low, like on Mars. In spring, as the ice grip loosens, the ground on the slopes is freed and slides downhill, raising clouds of red dust. On Mars, the northern polar ice caps shrink in the warmer summer when its northern hemisphere leans towards the sun. They grow again during the colder winter when the North Pole is oriented away from the sun. The same thing happens in the south. Mars and Earth are the only planets in the solar system with polar ice caps that wax and wane with the approach of winter and summer. So, the seasons on Mars vary like those on Earth. The seasons differ in length more than they do on Earth because the orbit of Mars has greater eccentricity than Earth's. For instance, northern hemisphere spring lasts for 194 sols, while fall lasts for only 142 sols. But when did we start to understand that Mars could be a planet similar to Earth? In 1840, Wilhelm Beer, a German banker and amateur astronomer, created the first maps of Mars with his colleague Johann von Madler. They reproduced the dark areas that remained in fixed positions, initially described as water basins. However, the spots had variable color and intensity, and in 1860, French astronomer Emmanuel Liais suggested they were vegetation, thinking the changes were due to the seasonal cycle. It was eventually discovered that they were changes in visibility caused by dust storms. In 1877, Italian astronomer Giovanni Schiaparelli mapped the surface of Mars, classifying the dark shapes as continents, islands, and bays. He also seemed to see numerous long, straight channels connecting some landscape features. Percival Lowell, an American businessman, invested his wealth in building an observatory in Flagstaff, Arizona, to search for Pluto and study Mars. He also saw the color changes in the dark areas and linked them to the changes in the polar caps. When a cap shrank, a dark, irregular greenish-blue band formed around the edge, which then disappeared as the cap shrank further. Then, a dark wave flowed into the channels towards the equator. It was as if a large amount of water was revitalizing the vegetation, just like the seasonal floods of the Nile Valley. Lowell was not familiar with Schiaparelli's map and hoped there was life on Mars. He interpreted Schiaparelli's channels as canals, meaning artificial constructions rather than natural formations. This led him to conclude that the canals were dug by Martians to create an irrigation system and alleviate the perennial drought by channeling water from the polar caps. The belief spread that Mars was a dying, arid world, but not only that. Fueled by novels like The War of the Worlds, it became a common belief that its inhabitants intended to invade and colonize Earth. Less fancifully, in 1877, American astronomer Asaph Hall discovered two satellites orbiting Mars. The larger inner moon is Phobos, fear, and the smaller outer moon is Deimos, terror. The satellites are named after the sons of Ares, who accompanied him in battle. Like Earth's moon, they revolve around their planet in the same time it takes them to rotate, so the same side always faces Mars. In that sense, they are moons, but otherwise they are very different from our moon. Phobos skims above Mars 3 times a day at a height of about 6,000 kilometers or 3,700 miles, while Deimos takes slightly more than a day to orbit Mars at about 23,000 kilometers or 15,000 miles above it, roughly 6% of the Earth-Moon distance. No other satellites in the solar system travel so close to their primary. Undoubtedly, a mission to either would find chunks of Mars in the form of meteorites. While both are cratered, Phobos boasts a crater nearly half its width. They contain too little material for their internal gravitational attraction to shape them into round worlds. Phobos also has grooves that may be the result of tidal stretching. The mean radius of Phobos is 11 kilometers or 6.8 miles, whereas Deimos is only 6.2 kilometers or 3.9 miles. In fact, they look more like captured asteroids than the Moon. Although today Phobos and Deimos can be seen occasionally eclipsing the Sun from the Martian surface, their sizes and distances prevent them from completely covering the solar disk. They are among the tiniest satellites in the solar system. Small as they are, their situation cannot last. Phobos is literally inching towards the Martian surface and cracking up. In less than 50 million years, Mars may lose a moon but gain a ring system. This discovery further reinforced the idea that Mars was a planet quite similar to Earth. But all this ended with the new century. In 1909, at Meudon, just outside Paris, observing the planet with a large telescope, Greek-born French astronomer Eugenios Antoniadis concluded that the channel should be considered merely an optical illusion due to the human eye's tendency to interpret point light, and dark spots observed with modest magnification through the Earth's atmospheric shimmer as geometric structures. There was, therefore, no truth in imagining a Martian civilization entirely devoted to building irrigation canals for the planet. Doubts that Mars could host changing vegetation continued almost to the present day, and only with the advent of the space age did the illusion of an inhabited world finally fall. The first mission to visit Mars was Mariner 4, which, after nearly 8 months of flight, flew over the planet on July 15, 1965, at an altitude of only 9,846 kilometers, continuing along the circumsolar trajectory it was on. During the closest approach, it transmitted 11 images of the Martian surface for about 25 minutes, and the 7th frame showed something unexpected. The planet's surface appeared completely arid and heavily cratered. These photographs dispelled any illusions of the presence of life forms, even if only plant life. The red planet thus became for everyone the dead planet. The first spacecraft to orbit Mars, and indeed the first to orbit a planet other than Earth, was Mariner 9, which arrived on November 14, 1971. At that time, a dust storm was raging across the entire planet, hiding its surface. The scientists saw nothing but a yellowish haze, and there were long faces in the control center at such bad luck. Dust storms are a frequent phenomenon on Mars. Often, they are small tornadoes, like those on our planet known as dust devils. On Mars, dust devils roam the desert, moving at high speeds and changing direction in a way that seems both intentional and wild. They stir up the ground, revealing the dark material beneath the red surface dust. From space, this dark material looks like a scribble in the desert, traced by the dust devil on its path. Martian dust storms can be much larger than individual tornadoes. Sometimes they are so massive that they are visible from Earth. They obscure topographical features and can last for months. They lift the lighter dust, and from the surface of Mars, they completely block out the sun. The winds carry the sand everywhere, covering the entire planet, including the polar ice caps, which take on a layered structure like a chocolate and cream cake. A layer of dust covers the ice, then the ice reforms and gets covered again. Dust storms occur mainly in summer when convective motions create strong winds that lift the dust. The most intense storms hit the planet's southern hemisphere. This is because when it's summer in the southern hemisphere, Mars is significantly closer to the sun than when it's summer in the northern hemisphere. Consequently, the southern summer is hotter, so the convective motions are stronger and create more powerful dust storms. Once started, the largest storms can last for weeks or months. Just like with Mariner 9, which had to wait patiently in orbit for the dust to settle, which happened too much later in mid-January of 1972. The long wait was rewarded, however. The probe revealed that the surface of Mars, contrary to what Mariner 4 had shown, which had evidently managed to photograph only a limited portion of the surface, had a certain variety. First of all, Mariner 9 identified recently formed volcanoes. The most impressive of these is Olympus Mons, standing 25 kilometers tall. Think of Everest, which at 8,848 meters is the highest mountain on Earth. Olympus Mons is nearly 3 times taller. The largest volcano on Earth by volume is Mauna Loa, which makes up most of the big island of Hawaii and rests on the Pacific Ocean floor. Well, Olympus Mons has a volume 100 times greater, and its size justifies its grand name, as in Greek mythology, Mount Olympus was the home of the gods. In the same region of Mars, the Tharsis region, there are several other volcanoes. All around, there are lava flows that look recent, perhaps only a few million years old, but no eruptions or active lava flows have ever been observed, and there doesn't seem to be any violent seismic activity either. Additionally, Mariner 9 discovered a massive tectonic rift, which was named Valles Marineris, Mariner Valley, in honor of the probe. The system stretches for 4,000 kilometers or 2,485 miles east-west along the equator, is 600 kilometers or 373 miles wide, and 7 kilometers or 4.35 miles deep. It's a complex of geological fractures 10 times longer, 7 times wider, and 7 times deeper than the Grand Canyon. It's the largest known structure of its kind in the entire solar system, extending for about a quarter of the circumference of Mars. However, Mariner 9 also showed that the most common terrain type on Mars is vast, arid plains of red or yellow, similar to the rocky deserts on Earth. A turning point in discovering many of the secrets of Mars came with the 2 Viking missions of 1975-1976. Each mission involved a spacecraft composed of 2 parts, a lander and a mother capsule that remained in orbit around the planet after releasing the lander onto the surface. The 2 landers were the first to touch down on Mars. Viking 1 remained operational for 6 years and Viking 2 for 3. They searched for biochemical traces but found none. The surface appeared sterile. It seems there is no life on the surface of Mars, or if there is, it doesn't have the properties tested by the landers during experiments conducted directly on the Martian surface. The big surprise came with the discovery that vast areas of Mars must have once been covered by water. The two missions demonstrated this by identifying geological structures that usually form in the presence of water. There were perfectly flat areas with enclosed basins. Evidently, this was material accumulated at the bottom of ancient lakes. The lakes had formed layers of clay. In common language, the word clay has a broad meaning, but in geology it has a technical significance that goes beyond the material's appearance. Later, those layers were studied with satellites orbiting the planet to determine their chemical composition, and it emerged that they were made up of minerals deposited by water, definitive proof that certain areas of Mars were once under still bodies of water. Other clues to the presence of water are the drop-shaped islands, elevated rock formations compared to the plains, extending downstream of obstacles like crater walls. The shores of those islands, now surrounded by arid land, look like cliffs hundreds of meters high, which must have been swept and eroded by devastating floods. Some plains also turned out to be scattered with rounded boulders, probably pushed and shaped by currents. Essentially, there was increasing evidence of abundant water on Mars in ancient times. Scientists have named this period the Noachian, inspired by Noah and the Great Flood. But where and why did all that water disappear? And more importantly, could this mean that Mars might have once hosted life? Questions that, at the time, had no answers. Starting in the 1980s, Mars exploration accelerated. Fewer launchers, but longer missions that made many more discoveries. Since 2010, there have always been 4 to 8 active vehicles on the planet and in its orbit. The ones that usually generate the most excitement among space mission enthusiasts are the rovers, which land on Mars and traverse its surface. The first ones were the size of a coffee table, while the current ones are the size of a car. The total distance they can travel has also increased from 100 meters to tens of kilometers. Communicating with Earth, the latest rovers can choose an interesting point to visit and reach it in a partially autonomous manner. This is a significant advancement because a radio signal can take up to 25 minutes to travel from Earth to Mars or vice versa, so it could take an hour from when the rover sees an obstacle to when it receives the command from Earth to go around it. The studies conducted by rovers over these decades include mapping the surface, analyzing rock composition, and investigating the atmosphere and magnetic field. Mars has a very thin atmosphere, with surface atmospheric pressure of about 0.6% of Earth's. However, it is sufficient to partially protect the surface from solar and cosmic radiation, and can be used for aerobraking maneuvers by spacecraft. The thin atmosphere is responsible for the surreal appearance of the Martian landscape due to the strange color of the sky. It is incapable of retaining blue and violet solar radiation, which makes Earth's sky blue. Additionally, frequent and violent dust storms leave a large amount of dust suspended, coloring the sky pink. Besides being thin, the atmosphere is also very shallow, only a few kilometers thick. Among the most curious discoveries, which long made people think of finding traces of life, is something related to the red color of the planet due to the layer of dust covering its surface, permeating the atmosphere and tinting the sky orange. The dust consists of various types of hematite, a red or orange iron oxide similar to rust. This mineral typically forms in water and has been found in abundance in the region of Mars called Meridiani Planum. In 2004, the rover Opportunity landed in that area to investigate, based on the assumption that if there was once abundant water, then perhaps traces of Martian life remained. Opportunity found areas covered with small spheres made of a type of hematite that forms in water and is less red than usual. When the photos taken by the rover were manipulated to highlight the spheres, the less red hematite turned blue, so the team nicknamed the spheres blueberries. Look at them. It seems impossible that they are just the result of a purely geological process. But speaking of life, there is a significant limitation to its emergence on Mars, represented by the fact that its magnetic field is very weak, almost non-existent. It generally has less than 1% of the strength of Earth's. It is particularly weak above the crust of the northern lowlands of recent formation, and also above large and deep craters and active volcanic areas. It is stronger above the ancient southern highlands, undisturbed by giant meteorite impacts or volcanism. On Earth, the magnetic field is an almost unnoticed presence. Yet the weakness of the magnetic field is why Mars, from a warm and water-rich planet, has transformed into a cold and arid place. Earth's magnetic field mainly derives from an internal dynamo produced by convective motions in the molten iron core. It surrounds Earth and its atmosphere, extending into space even beyond the Moon's orbit, up to 400,000 kilometers high. The volume it encloses is called the magnetosphere, and it is precisely thanks to this structure that the lethal particles emitted by the Sun cannot reach the surface of our planet. Our star is an immense thermonuclear furnace, continuously emitting enormous quantities of charged particles into space, the so-called solar wind. It is also agitated by gigantic explosions during which the solar wind is particularly dense, hot, and fast. After a few days of travel, the solar wind reaches Earth. The impact deforms Earth's magnetic field, confining it to a region called the magnetosphere, which manages to deflect it and keep it away from our planet, making it flow like river water around a bridge pillar. Without this protection, life would disappear in a few weeks. Mars once had a similar magnetosphere generated by a dynamo which magnetized the rocks. We know this because traces of residual magnetism have been found in the planet's oldest rocks. But then the dynamo stopped working. This happened because the convective motions in the molten iron core of Mars ceased. The reason for this interruption is a secret the planet has yet to reveal. Perhaps being very small, the core cooled quickly, becoming first viscous and then solid. Perhaps the internal structure of Mars is different from Earth's, and the mechanism that creates convective motions deep within Earth, whatever it is, does not exist on Mars. Whatever the reason, 4 billion years ago, the disappearance of the magnetic cover opened the doors to the solar wind, which, in addition to sterilizing the planet's surface with its ultraviolet rays and particle radiation, also began to carry away its atmosphere. This task was facilitated by the planet's small size, unable to retain it longer with its mass. There are studies showing that there are precise planetary size limits for supporting life. If planets are too small, gravity is insufficient to retain the more volatile molecules. This could mean that even the presence of an efficient magnetosphere would not have prevented the loss of the atmosphere. So, in the end, with almost all the atmosphere gone, the atmospheric pressure became too low to allow liquid water to exist on the surface. Now, Mars is an arid planet, swept by global dust storms. It is also a frigid world where winter night temperatures can drop to minus 140 degrees Celsius at the poles. It is the red planet we have come to know, a place that only robotic rovers find hospitable. Could there be a possibility of some liquid water pools on the surface? In fact, for there to be liquid water on the planet's surface, atmospheric pressure would need to be much higher than what it is currently measured. An exception could be the Hellas Planitia crater, which, being the largest and deepest crater on Mars, has a slightly higher atmospheric pressure at the bottom than the triple point. So when the temperature exceeds 0 degrees Celsius, it could contain liquid water. So, my friends, over time, if it had been fortunate enough to retain its magnetosphere, perhaps Mars could have hosted life, even alien creatures like those imagined by H.G. Wells. In that case, we might have truly faced a war of the worlds. But it didn't turn out that way. There remains the hope that in very ancient times, during the Noachian period, primitive forms of life developed that today survive in particularly ecological niches. That would indeed be a secret of Mars waiting to be unveiled. But perhaps there is something else that might give us the fortune to discover that Mars once teemed with life, maybe only at the level of unicellular organisms, meteorites. Because as you know, we now have the certainty that a large number of meteorites found on our planet's soil come from Mars. The history of Martian meteorites has been reconstructed by measuring radioactive elements and their decay products, which remain trapped in the rocks once they have solidified. It has been established that the rocks from Mars were last in a molten state 1.37 billion years ago, a much more recent time compared to most meteorites, which solidified 4 billion years ago or more. It also seems that all Martian meteorites come from a large fragment expelled into space 200 million years ago when an asteroid crashed into Mars. The impact probably also hurled a shower of smaller fragments into space. Perhaps this event caused the grooves radiating from Phobos' nose, or if not this, a similar one. The large fragment moved away from Mars and began orbiting the solar system like an asteroid. A collision with another asteroid 10 million years ago broke it into smaller parts. These fragments scattered in all directions, orbiting in space for another 10 million years, and recently some have fallen to Earth. This story shows that the planets of the solar system, although separated by tens of millions of kilometers, are not entirely isolated from each other. In reality, there are continuous exchanges of material between them. Lunar material falls to Earth in the form of lunar meteorites, and Earth's material is hurled to the Moon. Just as traffic flows both ways between Earth and the Moon, Martian material has fallen to Earth, and Earth's material has surely ended up on Mars. Therefore, a bit of the soil in your garden or the pot on your windowsill, just a bit, comes from Mars. The carrots you eat contain a pinch of the red planet. And just as there is a sprinkling of Martian soil on Earth, so too Earth's soil is found on Mars. Perhaps that soil contained organisms that developed in the favorable terrestrial environment. The most resilient could have survived in space, and the most resilient of all, after hitching an interplanetary ride and falling by chance into hospitable spots on the red planet, could have survived to colonize Mars. And who knows, if one day we find forms of life on Mars, we might discover to our surprise that they came from Earth, and that the Martians are us.